Okay, hi everyone. So I'm going to be talking about HFC blowing agents in insulation, which is one of the big blind spots within embodied carbon from my perspective. So before I kick off, I want to just to frame the discussion to get a sense of scale of how these embodied carbon emissions compares with operational carbon emissions on a whole building basis, and then we'll get deeper into the insulation numbers so you have some context. If you're not familiar, these are the different life cycle stages within LCA. And so many EPDs typically report A1 to A3, which covers raw material extraction or supply, transportation, and manufacturing and processing. So you'll see almost all EPDs cover that. Some EPDs may also cover some of these additional stages, like the use phase and the end of life phase. And this is particularly significant in the context of HFC blowing agents, because while for most products, the emissions typically, the bulk of the emissions, let's say 90+% of the emissions typically comes from the product stage. For XPS and for spray foam insulation, if they're using these higher global warming potential blowing agents like HFC, they actually have large sources of emissions, let's say in A5, in B1, and in C. So like as the blowing agent gets released throughout the lifespan of the building. So that's important context to keep in mind as we get into this discussion. As you're probably all familiar with, operational carbon emissions, we quantify that using energy modeling typically during the design phases of a project, and we use LCA to quantify embodied carbon. When we're talking about embodied carbon, we're typically referring to global warming potential, which is one of the multiple environmental impact categories that we look at when we're doing a life cycle assessment. GWP is typically the one that we're mainly focused on. And when we're talking about the blowing agents, the GWP factor, that's relative to CO2 emissions. So when we say, actually, I'll get deeper into this later. But yeah, this is the main one we're focusing on. Yeah, and historically, the thinking has been that most of the emissions in a building comes from the operational carbon emissions, associated with the energy usage of a building and operating the building, heating and cooling. But we're seeing, depending on where your building is and what the electricity grid carbon intensity is and how efficient your building is, over time, you'll see that the embodied carbon can become a bigger slice of a smaller pie. And so if you kind of put the embodied carbon and the operational carbon emissions, those pictures together, let's say the yellow representing the embodied carbon, the operational carbon emissions can be coming down over time. You can see like how these pictures compare. So let's put some actual numbers to it. You may have seen the Carbon Leadership Forum. They have a benchmark study, and they show a wide range in whole building LCA results in terms of embodied carbon intensity, so kilogram of CO2 per meter squared of floor area. And it can range anywhere from, let's say, below 100 to around 1,000, with many of them falling in the 200 to 600 range. Similarly, One-Click LCA also has a few benchmarks specific to different building types. So in this case, this is the office and apartment building types, and they create a letter grade rating system. So again, kind of keep these numbers in mind as we jump into that insulation conversation. So you can see, many of them, let's say 200 to 800, averaging around 400 or 500 kilograms of CO2 per meter squared. And I think this typically just focuses on the structure and the envelope of a building. It may not include some of the other elements like interior wall partitions and furniture, tenant improvements and mechanical, electrical, plumbing systems, the embodied carbon associated with all of that. So how does that compare with operational carbon metrics? So these are specific to BC, in Vancouver. We have the BC Energy Step Code. And so as we go higher in the steps, we have more and more energy efficient buildings. But it also depends on the fuel source. So are these gas, like natural gas buildings, or are they electric driven buildings like electric resistance or heat pump? In BC, we have very clean electricity, mainly from hydro. And so when we design our electric buildings, we can get them down to 1 to 2 kilograms of CO2 per meter squared per year. So obviously that's very, very low. We also have some benchmark, like measured GHGI numbers from buildings that currently exist in BC. We just released the first year of study. And so let's say on average, multi-unit residential buildings are around 21 kilograms of CO2 per meter squared per year, offices are around 15. So that gives you some context for operational. So And then, across different cities, you can see big differences. So I mentioned before, Vancouver, in BC, we have very clean hydroelectricity. If you're in a place like Calgary, where it has much colder climate, maybe the buildings aren't as energy efficient. Also, like they use a lot of fossil fuels in their electricity. So their electricity grid carbon intensity is much, much higher than Vancouver. You can see their GHGI numbers can be, let's say a baseline building would be 71, for example. So big ranges in the operational carbon emissions. So what happens when you put those two pictures together? So let's say this is actually a project that I'm working on, 5-story office building. The baseline building is 558 kilograms of CO2 per meter squared. So that's the embodied carbon. But then if you compare against, the typical average office in BC, if you're assuming that 15 number, you can see that over a 60-year lifespan for the building, it would be 40% embodied carbon, 60% operational. If you're comparing against the actual building that we're designing, which is an electricity-driven building, electric building, based on our energy modeling results, you can see even after 60 years, it'll be 90% embodied, 10% operational, because the operational is so low. And I think a similar dynamic may play out in Seattle as well. I'm not very familiar with the operational carbon intensity, but I think you guys have a relatively cleaner grid compared to other states in the US. So yeah, that may play out as well there in similar climates. So that's just to give some context to whole building LCA numbers. Now let's get into insulation and blowing agents. If you look at global greenhouse gas emissions annually, you can see how it's changed from 1990 to 2018. We're oftentimes focused on the CO2 emissions, but we also need to think about methane. And then there's the fluorinated gases, F gases. So when we're saying HFCs, which are used in some of our blowing agents, so hydrofluorocarbons, they belong to this F gases category. So you can see this slice is actually, even though it looks small, it's actually increasing quite a bit, quite rapidly. And so it's actually of all the greenhouse gases, the different types of greenhouse gases, it's the fastest growing one. So, depending if it's OECD or non-OECD countries, it's growing at a rate of, let's say 4 to 5% or 5.5% each year. And so this was a big cause for concern because HFCs, fluorinated gases, they're used as refrigerants in our mechanical system, but they're also used as blowing agents in our insulation. And a couple of years back, there was some projections that if we don't actually act on this alone could potentially increase global climate by 0.1 degrees Celsius by mid-century and 0.5 degrees by 2100. So very significant factor to look into. Now I'm going to get into kind of a geekier territory, which you may or may not recognize when you're thinking about these greenhouse gas emissions. Oftentimes people don't realize that there's an inherent time horizon that's included in all of the GHG emission statistics that you see, whether they're at the national inventory, GHG inventory level, to what's reported in our EPDs, to what we report in our LCAs. They're oftentimes assuming a 100-year lifespan. But the reality is that different greenhouse gases actually have different impacts on our atmosphere over time. So for instance, CO2 can stay in the atmosphere for a long time. Even after 100 years, there's about 44% of the CO2 that was emitted is still in the atmosphere, actively impacting global warming. Even after 1,000 years, there's 23% of the CO2 still remaining in the atmosphere. So how do you actually equate all these different greenhouse gases that aren't CO2 to something like CO2? Well, you have to assume an inherent time horizon. So for example, methane, you may have heard that methane is something like 25 or 28 times more impactful than CO2. Well, that's at a 100-year time horizon. But if you actually look at a shorter time horizon, let's say for 20 years, GWP 20 would say that methane is 84 times more impactful than CO2. So almost a 3x difference. And that's because methane doesn't stay in the atmosphere for as long. It has a atmospheric lifespan of something like 12 years. And this dynamic doesn't play out just for methane. It also plays out for refrigerants as well. So R134A, R410A, these refrigerants that we use in our mechanical systems and also that we use as our blowing agents can have a big impact. So for example, you can see for most of these HFCs, the atmospheric lifespan is usually less than 20 years, oftentimes less than 20 years. And so if you use a GWP 20 metric, which is also important in the context of avoiding our climate tipping points, which is a whole separate discussion, but if we're trying to prioritize near-term emissions reductions, these are even more important than we give them weight to, when we're typically calculating based on a 100-year time horizon. So most of the GWP numbers that you see are these GWP 100 stats. But if compared to GWP 20, you can see they're typically 2 to 3 times higher than the GWP 100 numbers. So that's just something to keep in mind when we're talking about blowing agents. And I've actually taken the CML inventory. So in North America, we use Tracy, but in Europe, they use CML. This is the characterization factors that we use to kind of equate different greenhouse gases into CO2 equivalents. You can see the GWP 20 versus GWP 100. For some gases, the GWP numbers are lower, some are much higher, so that's the red ones. I won't get into the details here, but so if you're trying to avoid near-term climate change, actually reducing these near-term climate forcers, things like methane and HFCs, can have a very quick impact on our climate. So for example, if you imagine every year you're growing a certain amount of methane gases and you're adding that methane into the atmosphere. And so like in the year 1 or year 0, you emit a pulse of methane, and then it takes 12 years to get to the half-life. It's decaying in the atmosphere, and then next year you emit a certain amount. This is what that dynamic looks like. But all of a sudden, if you stop emitting, it can very quickly reduce the concentrations in the atmosphere. So now let's get into EPDs, environmental product declarations. So EPDs, most of you are probably familiar with, but they're basically like nutrition labels. But instead of reporting the health impacts per unit of food, for building products, they report the global warming potential per meter cubed of concrete, for example. So these EPDs, they're third-party verified, they follow ISO standards, and it avoids some of the greenwashing that may be coming because it's actually evaluating the actual environmental performance. These EPDs can be both industry average values, so for a given product category, or it could also be manufacturer or plant or product specific EPDs. So the reason why I started looking into this HFC question was because of this book. So Drawdown, you may be familiar. It's a book that came out a couple of years ago. And what they tried to do was figure out what is the most impactful climate solution. So what's the biggest solutions, the top solutions globally over the next 3 decades that we can use to reduce or draw down carbon emissions. And so the top of the list was refrigerant management, which came to a surprise to a lot of people. It came out ahead of things like solar or wind. And so refrigerant management has a huge potential, 89 gigatons of CO2 reduction potential over the next 3 decades, which is equivalent to something like 1.5 to 2 years of global climate emissions, or global GHG emissions. And it's much higher than even alternative cement, which we give a lot of talk to when we're talking about embodied carbon. So when I was looking at the EPDs, this was a couple years back, but looking at Dow, which is now DuPont's styrofoam XPS EPD, I noticed that the installation and end of life, so the module B and module C stages, those emissions were quite high. Same thing with Owens Corning's older versions of the XPS. And oftentimes these EPDs, it's kind of hard to distinguish. You just see a table with scientific notation, and it's kind of hard to really see how significant are these numbers. And so I put them into an Excel spreadsheet. And so what I've done is I've looked at DuPont's XPS EPD, so both the older version, which is the blue XPS, and then their newer, lower global warming potential XPS installation, which is their gray one. You can see these. Generally speaking, the blue text refers to the HFC based installation, so kind of the older variety, the higher impact blowing agents. And then the red ones are the HFO or the, well, they may or may not be technically HFO, but they're lower global warming potential blowing agents. So you can see this is DuPont's numbers. This is Owens Corning's number. Owens Corning, this is their older version across different compressive strengths, which Stan was talking about earlier. And then same thing with their newer NGX EPD across different compressive strengths. I noticed that DuPont didn't actually specify a compressive strength, nor do they have a compressive strength factor that you multiply, but obviously at different densities, the XPS can change. And just through my calculations, I'm estimating that that's a rough, what they're reporting is probably around 35 PSI, but it's not explicitly stated in the EPD. So I was just trying to get a sense of how this compares with the Owens Corning numbers. But you can see it's broken down by A1 to A3, A4, B1 and C. So you can see the module B and module C. So during the use and end of life stages, huge amount of emissions, right? It's not just this, whereas most products, most of the emissions are on the A stage. So if you add it all up, this is what the total number looks like per RSI equal to 1, which is roughly equivalent to an R 5.7. So, and one really important factor, which I kind of highlighted and brought to the attention for a lot of people in the industry, I think it was like last year, was, or maybe the year before, as some of the whole building LCA software tools, actually the three main ones that are typically used, Athena, Tally, One-Click LCA, those XPS values were significantly lower compared to these manufacturer-specific EPDs that were out there. And there's not that many XPS manufacturers in North America. So their XPS in Athena, they were assuming a GWP of, about 4 kilograms of CO2 per meter squared. Whereas you can see, some of these HFC-based ones are much, much higher. So they're about 10 to 25x higher than what's shown in our whole building LCA tools, which it has significant implications. Because if you think about our benchmarking efforts, our previous LCA studies, if they use a lot of XPS or they use a lot of spray foam, they probably significantly underestimated the scale of those emissions. So this is breaking it down across the different life cycle stages. The next chart I'm going to show is just showing you a kind of a summary at different R values. So this is looking at module A to C, so totaling it all up. And then at different R values from R5 to R60. So in the context of XPS, it's like R5 per inch. So that's 1 inch of insulation all the way to 12 inches of insulation. And I'm showing it not just for XPS and spray foam, but I'm also showing it for EPS at different compressive strengths, polyiso, mineral wool, fiberglass, and cellulose down here. So you can see the scale of emissions, how they compare. And generally speaking, if you just look at this graph, it's overwhelming. The XPS and spray foam are much, much higher than some of the other insulation types. Obviously, there are differences amongst these, but this just gives you a sense of how significant these numbers are. So if you can imagine, like I've actually had projects specify 8 inches of XPS or even 12 inches of XPS on the roof. They can get up, if you're using the traditional XPS that was available prior to this year, those insulation values can be, 400, 500, 600 kilograms of CO2 per meter squared. So that's on the scale of an entire building, which gives you a sense of how significant these emissions are. Now, it's great that there's a new batch of products coming out. So if you have to use XPS or spray foam on your projects, I strongly, strongly recommend you actually specify that you want the lower global warming potential blowing agents. And so for Owens Corning, when they released their NGX EPD, they showed, I believe, an 83% reduction in GWP. It's important to note that, so in Canada, there has been regulation that's been put in place that's been coming into effect at the beginning of this year. And they were limiting the blowing agents to a GWP of 150. But I later realized that they actually gave some exemptions out to a few companies at different dates. So they could still kind of use global warming potentials of like 750 or 550, up to the end of the end of this year or next year, depending on the manufacturer. So it's something to keep in mind. This was from Owens Corning's site. So you can see all of Canada is covered with regulation. Some other states have final laws and regulations in place, and some other ones have proposed laws and regulations. So, with final laws, there's Canada, California, Colorado, New Jersey, New York, Vermont, Washington, Maryland, Massachusetts, Delaware, and then proposes Hawaii, Maine, Virginia, Rhode Island. So, if you're also doing projects that aren't in these regions, then I would really strongly specify that make sure that the XPS and the spray foam that's coming on your projects don't have those blowing agents. This is one of the big blind spots that I think we've discovered in insulation, but within the field of embodied carbon, there's other blind spots that we need to tackle. And I have a sense that as we start to tackle these blind spots, we may see the total absolute values for our embodied carbon on a whole building basis, like slowly increase. But it's also more opportunities to reduce our emissions as we discover these things. That's it for my presentation. Oh, this is a map of the 31 hubs around this. So you guys are part of Seattle, but in case you're curious, there's many hubs around the world as well. And yeah, so if you need help on whole building LCAs on your projects or have some specialized projects, sometimes we take on policy and research type projects relating to embodied carbon, we'd be happy to help out and happy to take questions from here. Thanks.